This video goes over trigonometric ratios and angles in standard position. So let's start off by just remembering our primary trig ratios. If angle C is our theta here, we've got our opposite side, we've got our adjacent side, and our hypotenuse. Our primary trig ratios are sine theta is opposite over hypotenuse, cos theta is adjacent over hypotenuse, and then tan theta is going to be opposite over adjacent. We also have the angle of elevation, which is the angle measured up between the horizontal and the line of sight from an observer to an object. So that would be here is the angle of elevation if the observer was here. Our angle of depression is measured from the horizontal down, this angle right here, and this would be where the observer is, up here. So let's do an example here. Find theta to the nearest degree. So if we work backwards, I'm looking at my theta triangle. Really, if I knew what this side length was, little side b, I would be able to solve for theta. So let's take a look at my other side here. What I notice is that I can use the information that I'm given to actually solve for little side d, which is equal to little side b. So the first thing that I'm going to do is use my sine ratio. So sine d is my opposite side, which is little d, over my hypotenuse, which is 10 here. And I can actually substitute in my value for angle D as well, which then allows me to solve for D. I've got 10 sine 70, which gives me D is about 9.4 meters. Now I know that D is equal to B. I already said that above. So now I can move on to my second step, which is using my second triangle. So looking at my theta, which is in A, I would have my adjacent side would be the 9 meters and my hypotenuse would be B. So I'm going to use the cosine of angle theta is my adjacent side over my hypotenuse, which is B or D. And then I'm going to do cosine theta is 9 over 9.4. Remember to solve, I'm going to do the opposite operation, which is taking the cosine inverse of both sides. This is going to work out to about 16.7, which means that I can say that theta is approximately 17 degrees. Usually when we're rounding angles, we go to the nearest degree. Okay, so let's do another example of a word problem. Here we've got two office buildings are 42.3 meters apart. So I'm going to draw a diagram to represent this situation. And I know that they are 42.3 meters apart. From the top of the shorter one, the angle of elevation to the top of the other is 27.5, while the angle of depression to the base is 78.2. Let's add some proper degrees symbols in there. So my angle of elevation to the one at the top is here, is 27.5. And my angle of elevation, which is from the horizontal down, is 78.2 here. What I'm looking for is to figure out the height of each building. So the first one that I'm actually going to find is, well, let's maybe put some labels in here. So y, and I'm going to represent this as x, and then I'm going to define my variables. So let's let y represent the height of the shorter building. And then we will let x plus y represent the height of the taller building. So the first thing that I'm going to do is figure out, well, it doesn't really matter. I'm going to start with x because that's at the top of my triangle. And what I'm going to use to figure out x is this angle and this triangle right up here. So I'm going to say that tan of my angle of elevation, 27.5, is equal to x over 42.3. Because the buildings are the same distance apart, I also know that this adjacent side in this case is 42.3 meters. This is going to allow me to solve for x. It's going to give me about 22 meters. Now I'm going to do almost the same thing. I'm going to solve for y. I'm going to use the second triangle right here and my angle of depression to allow me to solve for y. So actually the same trig ratio, tan of 78.2 is y over 42.3. Solving for y is going to give me 42.3 times tan of 78.2, which is going to give me approximately 202.5. So let's round that to 3 significant figures, which is 203. And I'm just going to go back. I didn't write in this step here. So tan 27.5. There we go. Okay. And then my y value is going to be 203 meters. So what I can see is, therefore, the height of the shorter building is 203 meters, and the taller building is 225 meters tall. Just adding those two together. Good example of an application problem using angles of elevation and depression. So let's move on to angles in standard position, which should be somewhat new. Okay, we're going to let P at x, y be any point on the terminal arm of an angle theta in standard position, r units from the origin. So that means that this length is r right here. If I draw my triangle, this length is going to be x, and then this length is going to be y, and I know that this is a right-angled triangle. So I can rewrite my primary trig ratios as sine theta is my opposite over hypotenuse, cos theta is my adjacent over hypotenuse, and tan theta is going to be my opposite over my adjacent. So the big question is, how can the measure of r be found? Well, we're looking at a right angled triangle. We know the Pythagorean theorem, so we can use that to find r. This next part is important. If the terminal arm lies in quadrant 1, so this is quadrant 1 here, then theta is the value found using the previous trig ratios. However, if the terminal arm lies in one of the other quadrants, so 1, 2, 3, or 4, then our principal angle is actually going to use something called a related acute angle. So when we find our trig ratios, we are going to find our related acute angle here, but our theta is really measured from our x equals 0 position all the way to this value. So we'll call this just theta 2. And here, our principal angle, or our theta 2, is going to be 180 degrees, subtract our related acute angle. In quadrant 3, our principal angle, or theta 3, I'm going to draw a little diagram here. Whoop. This is our related acute angle. This would be theta 3, all the way measured from that x equals 0 position. Our principal angle, or theta 3, is going to be 180 degrees plus our related acute angle. And then finally, if we're in quadrant 4, all the way around, our principal angle, or our theta 4, is just equal to 360 degrees, take away our related acute angle. So that is going to be important to remember, and let's take a look how that works out in our next example. So example 3, we're going to find the primary trig ratios and the principal angle given that the point P is on the terminal arm of an angle theta in standard position. So the first thing I'm going to draw is sketch where P is. I've got 7, 24. So I've got X is 7, Y is 24. I need to figure out what my R value is. So I've got R squared is 24 squared plus 7 squared. R squared is going to be equal to 625, which means that R is equal to 25. So once we have that, now we can write out our primary trig ratios. We can find sine theta, which I should label right here, is my opposite over my hypotenuse. My cos theta is my adjacent over my hypotenuse, and my tan theta is going to be the opposite over my adjacent. The last thing that I'm asked to do is to find my principal angle, so I actually want to know what theta is. So my principal angle is going to be the sine inverse of 24 over 25. You could use any of the other ratios in this case. And that's going to give me about 74 degrees. So let's find it, we'll say, to the nearest degree. Okay. So now let's look at another example where our standard, or our terminal arm, doesn't lie in quadrant 1. So here I'm going to look at the point -3, -9. So here I am all the way over in quadrant 3. I've got -3, -9. I'm looking for my R value, so I'm going to use the Pythagorean theorem. So R squared is -3 squared plus -9 squared, which is going to give me the square root of 90. Okay, I'm not going to reduce it because I don't really need to. I'm just going to leave it as that exact value. So the next thing that I'm going to do is write out my primary trig ratios. So sine theta is, right, and here's my theta that I have, is my opposite over my hypotenuse. My cos theta is my adjacent over my hypotenuse. And finally, my tan theta is my opposite over my adjacent, which actually happens to be equal to 3. So now I've stated my 3 trig ratios, and I'm going to now find out what my angle is. Now when I use my inverse, I am finding this angle right here. That is not actually the angle I'm looking for, which is this whole thing right here. That is my principal angle that I actually want to figure it out. So at the end, I'm going to have to do 180 plus my theta, which is my related acute angle, to get that figured out. So let's solve for that in red. And I'm going to use my positive ratio here to make sure that I don't get anything funny happening. So tan inverse of 3. So now I know that my related acute angle is going to be about 72 degrees. Now I can find my principal angle by using 180 plus 72, which gives me a principal angle of 252 degrees. So there's an example of finding the primary trig ratios and principal angle of an angle in quadrant 1, and then of an angle in quadrant 3.